So I want you to close your eyes for a second and just imagine utter enveloping darkness.
Yeah, it's like you're suspended in this encompassing heavy warmth that just presses against you from every single side.
Exactly. You're curled up, tight and compact, folded into this impossibly small leathery sphere.
And you've been here for what feels like an eternity, really, just kind of lulled by the faint rhythmic vibrations of the earth right above you.
Right. But then suddenly something shifts in all that stillness. The temperature around you drops just a tiny fraction of a degree as night falls above.
And this vibration hums through the cramped space. It's like a biological alarm clock that is hardwired right into your DNA
Yeah, this instinctual, just undeniable urge to move.
to push upward. And you feel this tiny sharp ridge on the tip of your snout, your egg tooth.
Right. And you scrape it against the leathery ceiling of your little world, tearing this jagged hole, and the fluid drains away,
Replaced by the coarse, heavy sensation of sand just collapsing inward on you.
which sounds terrifying, honestly.
Oh, absolutely, because all around you in this suffocating darkness, you feel the frantic scratching and wiggling of dozens of others.
Your siblings.
Yeah, moving in this chaotic unison. You are suddenly part of a buried avalanche pushing upward through the heavy grains.
You're fighting gravity. You're fighting the exhaustion that's just burning in your tiny muscles.
And you climb over the shells of your siblings, forming this, like, living elevator of flippers and snouts.
Until suddenly, the pressure breaks. You burst into the open.
And that sudden cool breeze of the night air hits your face, totally clearing away the humid, stagnant air of the nest.
You can actually smell the sharp, metallic tang of the salt spray. And in the distance, you feel the rhythmic, thudding vibration of crashing waves just shaking the beach.
And right above you, this brilliant glow reflects off a vast, moving expanse of water. It's the moon.
Yeah, acting as this celestial beacon, and its silver light is just pulling you forward.
So you begin this frantic, totally exhausting scramble across the slanted ground. The sand is dragging at your belly.
And every instinct tells you that lingering on this open expanse means certain death, right?
Right.
I mean, the shadows of seabirds are looming.
Ghost crabs are darting from their burrows. It takes literally everything you have just to move a few agonizing inches.
Your tiny flippers are propelling you like clockwork.
But then a cold, wet rush sweeps over you. The heavy gravity of the land just vanishes entirely.
Replaced by this buoyant, weightless, fluid embrace, you are in the ocean.
The first few years of your life are just this grand, sweeping drift. You are swept up by invisible underwater highways.
Floating endlessly, just letting the massive currents carry you across thousands of miles of open blue.
Yeah, this is your pelagic stage, the lost years.
And you learn to hunt for the translucent, pulsing shapes of jellyfish, siphonophores drifting in the water column.
You snap at them, feeling the soft, gelatinous yield of your food. You're sustained by this endless bounty of the open sea.
But one day you see a pulsing sheep that, well, it doesn't move quite right.
No, it doesn't. It's brightly colored, contrasting sharply with the muted blues and greens of the ocean around you.
And it's unnervingly still, you know. It doesn't pulse with that rhythmic grace of a jellyfish.
So you swim closer, totally guided by millions of years of foraging instinct, and you take a bite.
But it doesn't smell like food. It lacks that rich amino acid scent of prey.
And as your powerful jaws close around it, it just feels strange. It is rigid, unyielding, and totally foreign to the bite.
Because you aren't a human explorer. You aren't a submarine pilot. You are a loggerhead sea turtle.
And you have just taken your first bite of a world you cannot possibly understand.
Welcome, everyone, back to Saltwater Stories. Today, we are following our young loggerhead turtle as she navigates an invisible floating world that connects every single drop of the ocean.
It really is a grand wildlife journey filled with mystery and awe and the profound interconnectedness of nature.
We're going to trace the unseen currents that shape her life and discover how the story of the ancient ocean is just so intimately tied to the story of the modern land. Because, I mean, when we typically imagine the challenges a sea turtle faces, we naturally think of the massive cinematic threats.
Oh, for sure. You picture the shadow of a tiger shark cruising the reef.
Or the devastating power of a Category 5 hurricane churning up the coast. But there is a silent, almost imperceptible challenge out there.
Yeah.
How does something completely invisible, something that shouldn't even exist in her world, become the single most pervasive hurdle in her entire ocean journey.
To understand that, we really have to look much closer at what she just bit into.
Right.
So let's return to her perspective for a second. She is drifting on the surface of the water, a few years older now.
Her shell, which used to be soft and dark, has hardened into this beautiful golden brown armor.
And she's skimming a line of sea foam right where two currents converge, snapping at what looks like these clusters of tiny fish eggs.
They're small, about the size of a lentil, just bobbing gently on the surface.
But when she crunches down, fully expecting a pop of protein, they are hard as pebbles.
Yeah, those little pebble-like morsels she is eating are actually called nurdles. And they are the raw 3 to 5 millimeter building blocks of virtually everything synthetic in our modern world.
Precisely. I mean, before a water bottle or a dashboard or a medical syringe becomes the object you recognize, it starts as a nurdle.
Just a tiny piece of plastic.
Right. Industrial chemical plants manufacture trillions of these tiny raw polymer pellets, usually polyethylene or polypropylene.
They're basically the essential currency of global manufacturing.
Exactly. Factories buy them by the ton, they melt them down and inject them into molds.
And because they are the foundational material, trillions of them are shipped globally on these massive cargo vessels.
Stacked in containers, loaded onto trains, pumped into trucks. And the scary thing is, at every single transfer point in that vast logistical web, spills happen.
Yeah, I was actually reading the maritime incident reports on the Express Pearl, and the sheer scale of one of these spills is just staggering.
Oh, it's unbelievable.
In May of 2021, this massive cargo ship caught fire and sank off the western coast of Sri Lanka.
Right, and we always hear about oil spills, which are awful. And yes, it leaked bunker fuel, but the real catastrophe was in the cargo holds.
Because the ship was packed with roughly 1,680 tons of these nurdles.
The math on that is almost incomprehensible. We were talking about an estimated 70 to 75 billion individual plastic pellets pouring into the Indian Ocean from a single shipwreck.
Wait, 75 billion from one ship?
From one ship. And it completely suffocated the coastline. They washed up along more than 1,500 kilometers of Sri Lankan beaches.
Wow. And the local biologists on the ground, notably Dr. Usha DeVos and her team, they worked tirelessly to track this devastation.
Yeah, because you can't just scoop this up with a net, you know?
No, the nurdles just mixed into the sand, mimicking the exact shape and size of the organic matter the local wildlife relies on.
So you had dead turtles, dolphins, and countless fish washing ashore with their digestive tracts completely impacted.
And beyond the biological tragedy, the human element was just immediate and devastating.
Totally. The local artisanal fishing economy completely collapsed overnight.
Fishers couldn't cast their nets because they would pull up nothing but this synthetic snow.
Right. The nurdles coated the gills of fish and smothered the nearshore breeding grounds. It was this acute, highly visible disaster that basically laid bare a process that is usually totally invisible.
Yeah, because a massive spill like the Express Pearl is just the loudest version of the problem. Right?
Exactly.
To really grasp what our loggerhead is swimming through on a daily basis, we have to look at the entire physical spectrum of this foreign material in the water.
We can't just look at nurdles. We need to look at what scientists call the plastic family, categorized by size.
I love that analogy. It's a very helpful way to visualize it.
Right. So let's use a scale we can easily picture. If a piece of macro debris, say an intact 2-liter soda bottle floating on the surface, is the size of a basketball.
Okay, a basketball.
Then a large microfragment, like the lentil-sized nurdle our Curdle just bit, is roughly the size of a grain of rice sitting on a gymnasium floor.
Wow, okay. So we go from a basketball down to a grain of rice.
Yep.
But the physics of degradation dictate that the process doesn't just stop at the rice grain. It has to keep fracturing. Are we looking at a situation where these fragments eventually become completely invisible?
Exactly that. The next step down is the small microfragments. Compared to our basketball, this is a speck of flour dust.
A speck of flour.
Yeah, we are talking about fragments between 1 micrometer and 1 millimeter. They are easily inhaled by small marine organisms.
And then at the very bottom of the scale, we find the nanoplastics.
The truly invisible realm, completely imperceptible to the naked eye.
Which is terrifying.
It is. I mean, a single nanoplastic particle is smaller than a bacterium.
Wait, smaller than a bacterium?
Yes. To put that in perspective, if you took 1,000 of these nanoparticles and lined them up edge to edge, the entire line could fit comfortably on the period at the end of a printed sentence.
That is mind-blowing. Which raises a fundamental mechanical question, though. How does a structurally sound basketball-sized bottle even become a speck of flour.
Right.
I mean, the ocean water itself doesn't have the chemical ability to dissolve this material, right?
No, it doesn't dissolve like sugar or salt. The process is entirely mechanical and solar. It's called photooxidation.
Photooxidation.
Yeah. When that soda bottle floats on the surface, the sun's intense ultraviolet rays bombard the polymer chains.
Ah, so the sun's breaking it down.
Exactly. The UV radiation essentially bakes the material, breaking the chemical bonds and making the plastic incredibly brittle.
Okay, that makes sense.
And at the same time, you have the pounding kinetic energy of the waves and the corrosive nature of the salt water relentlessly attacking its surface.
So it's essentially weathering, like a mountain turning into sand, but happening in a fraction of the time.
Precisely. Over weeks, months, and decades, the material fractures. It cracks along these microscopic fault lines and splinters into smaller and smaller pieces.
But the crucial distinction here is that the molecular material never actually goes away.
No, it doesn't. Nature just doesn't possess the specific chemical enzymes required to digest and metabolize these synthetic polymers quickly.
It just shrinks.
It shrinks, becoming easier and easier for smaller and smaller animals to swallow.
Okay, but hold on a second. If our loggerhead turtle is swimming hundreds of miles away from any major human settlement, out in the vast open blue of the pelagic zone,
Yeah.
where is all this continuous tiny material coming from? Are cargo ships just constantly dropping nurdles every day?
Well, while maritime spills are definitely a factor, they are really only a fraction of the story.
Okay.
To truly answer that, we have to look back at the land our turtle left behind when she hatched on that moonlit night. We have to trace the water upstream.
So let's follow her as she swims closer to a coastal estuary, where a major continental river meets the sea.
The environment around her changes drastically.
Right. The clear, deep blue, nutrient-sparse water of the open ocean suddenly collides with this massive, murky brown plume rushing out from the river mouth.
And the current is powerful, carrying fresh water, sediment, and this strange invisible dust from a sprawling metropolis hundreds of miles inland, flushing it all straight into the sea.
So that river plume is basically the great global conveyor belt.
It really is. About 80% of all this synthetic material in the ocean originates directly from the land, not from the maritime industry.
80%.
Yeah. And the delivery system is highly concentrated. Studies show that just 1,000 of the world's rivers are responsible for carrying roughly 80% of this terrestrial runoff into the global ocean.
I think when most people picture river pollution, they picture someone tossing a plastic bag or a water bottle off a bridge.
Right, the visible litter.
Exactly. But the reality is far more insidious. The sources of this runoff are incredibly sneaky, hidden right inside our most mundane, everyday routines.
We really have to look at the mechanisms of our daily lives. Take tires, for example.
Oh yeah, I was digging into the friction mechanics of driving. It's wild. Every single time a car brakes at a stoplight, accelerates onto a highway, or turns a sharp corner, mechanical shear force occurs between the rubber and the asphalt.
It acts exactly like a coarse cheese grater on a block of cheese.
Such a good visual. Microscopic synthetic rubber dust is violently sheared off the tread of the tire.
And when you multiply that microscopic friction by the estimated 1.4 billion vehicles operating on the planet right now,
Oh, wow.
yeah, that invisible dust adds up to an unfathomable volume. We are looking at an estimated 6 million tons of microscopic tire wear particles generated globally every single year.
6 million tons. Just from driving.
Just from driving, it coats the highways, and when the rain comes, it washes all that synthetic rubber dust directly off the streets, down into the municipal storm drains, and flushes it straight into the rivers.
And it's not just inert rubber, is it? It carries an incredibly complex cocktail of chemical additives with it.
That's the scariest part.
Yeah, there's a specific chemical called 6-PPD, which tire manufacturers add to the rubber to prevent it from cracking under ozone exposure.
Right, it's a preservative, basically.
But when 6-PPD reacts with the ozone in the air, it transforms into a highly toxic byproduct called 6-PPD-quinone.
And biologists recently discovered that when this specific chemical washes into streams, it triggers sudden mass mortality events in coho salmon.
It's awful. It essentially causes their vascular systems to leak. It's highly lethal, and it comes from simply driving to the grocery store.
It is a profound realization that our terrestrial commutes are directly dictating the health of coastal ecosystems.
Totally.
And it's not just our cars, it's happening inside the sanctuary of our home.
Oh, right, the washing machine.
Yes, consider the washing machine. Inside that spinning drum is a hidden violent storm.
Because the majority of global textiles produced today, roughly 60%, are made of synthetic polymers like polyester, nylon, and acrylic.
The classic fleece jacket.
We all have one.
Exactly. We wear them because they are soft and warm. But that softness comes from millions of tiny plastic threads teased out to mimic wool.
And because of their fuzzy, loosely woven texture, when a synthetic fleece jacket tumbles in the hot, soapy, abrasive environment of a washing machine, the mechanical action breaks thousands of those tiny fibers loose from the garment.
A single load of synthetic laundry can easily release over 700,000 microscopic fibers into the wash water.
Wait, 700,000 fibers from one cycle?
From one single cycle. And they are microscopically thin, often a fraction of the width of a human hair.
So when the washing machine drains, those fibers slip right through the internal lint traps.
They bypass the filtration grids of many municipal wastewater treatment plants, and they flow effortlessly out into the river plume that our turtle is swimming through right now.
Man. So when she glides through that murky river mouth, she is not just swimming through discarded trash.
Yeah.
She is quite literally swimming through the remnants of our morning commute and the invisible exhaust of our laundry day.
It's wild to think about. And we cannot leave the shoreline without mentioning the single most ubiquitous piece of litter found on beaches worldwide.
Cigarette filters.
Yeah. The Ocean Conservancy's international coastal cleanups routinely rank them as the #1 collected item.
I read an estimated 4.5 trillion cigarette butts are flicked onto streets and beaches globally every single year.
4.5 trillion, and there is this massive public misconception about them.
Right, because many people assume the filters are made of a natural biodegradable material like cotton or paper.
Which is exactly why they feel comfortable just tossing them on the ground.
But they absolutely aren't. They are manufactured from a synthetic polymer called cellulose acetate.
Yeah, they are densely packed with thousands of tiny plastic fibers designed to trap tar.
And when they hit the environment, they don't biodegrade, they photodegrade.
Just like the bottles.
Exactly. Breaking apart into thousands of microscopic microfibers while simultaneously leaching trapped toxins like arsenic, lead, and nicotine directly into the water column.
So that single murky river plume we are observing is basically an environmental superhighway carrying pulverized tire rubber, synthetic clothing fibers, and toxic cigarette filters.
Just dumping them all in a massive concentrated dose into the fragile coastal waters.
But here is where the physics of the ocean take over.
Right, because how does all of that localized coastal pollution spread across the entire planet? I mean, if the river just dumps it at the coastline, shouldn't it all just stay trapped near the beach, sinking into the mud?
It would, well, if the ocean were a static pond. But the ocean is in perpetual restless motion.
Always moving.
Always. The moment those particles leave the mouth of the river, they are swept up by coastal currents and eventually captured by the great slow-motion whirlpools that dominate our planet's oceans.
So let's return to the sensory world of our loggerhead turtle. She is caught in this massive, sweeping current, drifting far from the murky coastline.
She rides this oceanic conveyor belt for weeks, traveling into the calm, windless, deep blue center of the North Pacific.
And the sheer isolation is breathtaking. At first glance, the water around her looks perfectly clear, a pristine cobalt blue.
But as she opens her beak to take in a mouthful of seawater, we realize the water is actually filled with an invisible peppery soup of suspended synthetic particles.
She has entered one of the 5 major ocean gyres.
Right. These are colossal, circular current systems, massive vortices driven by global wind patterns, and the Coriolis effect of the Earth's rotation.
They act like slow-moving centrifuges.
Exactly. Everything that floats, whether it's seaweed, driftwood, or synthetic polymers, eventually gets pushed toward the calm, high-pressure centers of these gyres.
You know, this is the perfect moment to completely dismantle a massive public myth.
Oh, please do.
When people hear the term Great Pacific Garbage Patch, they instantly picture a solid floating island of trash.
They do. They picture a dystopian landfill bobbing in the middle of the ocean.
Right, something so dense you could walk on it, or spot it easily from a satellite in space.
I am so glad you brought that up because that image is entirely inaccurate and it really hampers our understanding of the real crisis.
It's not a solid island at all.
Absolutely not. It is a vast, diffuse region, roughly twice the size of Texas, containing an estimated 1.8 trillion highly dispersed fragments.
I heard a fantastic analogy to help visualize this. Imagine filling an Olympic-sized swimming pool with crystal clear water.
Okay.
Then, take a pepper shaker and grind black peppy over the surface for an hour.
That's a lot of pepper.
Yeah. From a distance, standing on the pool deck, the water still looks perfectly clear and blue.
Right.
But if you walk up and scoop a single cup of water out of that pool, every single cup will have tiny flakes of pepper suspended in it.
That is the reality of the Great Pacific Garbage Patch. It is a massive three-dimensional soup of microfragments.
The soup.
Yeah, and in that soup, biological interactions are happening on a microscopic level.
Okay, let's look closely at a tiny blue fragment our turtle just brushed her flipper against. It's floating near the surface, but it doesn't look like a clean piece of plastic anymore.
No, it looks a bit fuzzy, its edges blurred, and it is coated in a strange, slick, living slime.
Which brings us to a truly fascinating, almost science fiction level discovery by marine microbiologist Dr. Eric Zettler.
Oh, this is so cool.
Yeah, he and his colleagues identified an entirely new ecological biome. They named it the plastosphere.
The plastosphere. It is a remarkable phenomenon. When a clean, sterile fragment of synthetic polymer enters the ocean, it doesn't remain sterile for long.
Within mere hours, opportunistic marine bacteria attach to its surface.
Because in a turbulent, vast ocean, a solid hydrophobic surface is prime real estate. It's like tiny microscopic pioneers arriving on a barren floating island.
And they secrete sticky compounds to anchor themselves, building a microbial city.
And once the bacteria lay the foundation, larger organisms move in. Single-celled diatoms arrive, then microscopic algae, and eventually tiny invertebrate animals.
The piece of trash is literally transformed into a microscopic, floating artificial reef.
Precisely. A complex, living biofilm forms over the entire fragment. But this thriving biological community creates a fatal mechanical change for the fragment itself.
How so?
Let's say that piece of blue plastic is polyethylene, a lightweight polymer that naturally floats on the surface. As the biofilm grows, it gets heavier. This process is called biofouling.
Ah, so the living slime physically adds mass and alters the density of the fragment.
Exactly. The added weight of the biological community overcomes the natural buoyancy of the plastic.
Wow.
Eventually, this once floating piece of material becomes too heavy, and it begins a slow, inexorable descent, dragged down from the sunlit surface into the freezing, crushing depths of the deep ocean.
Okay, wait, let me push back on this for a second.
Sure.
If these floating fragments are actually providing new, stable homes for bacteria and fostering the creation of tiny, thriving artificial reefs, is that inherently a bad thing?
From a purely biological standpoint, you mean?
Yeah, life is finding a way to utilize a new substrate. What is the harm when our loggerhead turtle, or the small fish she relies on, swallows this fuzzy blue speck?
That is a brilliant question, and it leads us directly into a dangerous, invisible, biological game of tag.
A game of tag.
Yeah. To understand the danger, we have to shift our perspective for a moment and look at the intricate microscopic food web surrounding our turtle.
Okay, let's zoom in on a microscopic copepod drifting just inches from her shell.
A copepod is a tiny, teardrop-shaped crustacean, a foundational piece of zooplankton.
And it is hunting for phytoplankton microscopic algae.
Right. So the copepod senses a nanoplastic particle drifting by.
Because that plastic particle has been drifting in the plastosphere, it is heavily coated in a rich biofilm of algae and bacteria.
And to the copepod's chemical receptors, it smells, tastes, and feels exactly like a delicious, nutritious meal.
It is a perfect chemosensory deception.
It is. So the copepod swallows the plastic.
And that single action sets off a devastating chain reaction.
A few minutes later, a small forage fish, like a sardine, comes along and eats 100 of those copepods in a single gulp.
And because the plastic is indestructible to their stomach acids, the sardine now has 100 toxic particles in its gut.
Then a larger predatory fish, like a mahi-mahi, eats 10 of those sardines, swimming right past our loggerhead turtle's nose.
Meanwhile, look to the sky directly above the gyre. A magnificent Laysan albatross, a seabird with a staggering 6-foot wingspan, is gliding effortlessly on the thermal currents.
It drops down and skims the surface of the water with its hooked beak.
It is visually hunting. and it spots a cluster of brightly colored red and orange fragments bobbing on the surface.
Mistaking them for a cluster of squid or nutrient-rich fish eggs, it scoops them up and swallows them whole.
Then that albatross flies thousands of miles across the ocean, returning to Midway Atoll, a tiny remote speck of land in the middle of the Pacific Ocean, to regurgitate that hard-won meal into the waiting mouth of her fluffy, demanding chick.
What we are witnessing across both these scenarios is a biological process called trophic transfer.
Trophic transfer is essentially a set of biological Russian nesting dolls. But instead of just one doll fitting neatly inside the next, it's 100 toxic dolls packed tightly into one, transferring up the food chain.
That is the perfect analogy. It's like a game of tag, where you don't just pass it to one person, you pass it to everyone you touch. And the concentration multiplies exponentially at every single trophic level.
Wow.
The Coke pod has 1 particle, the sardine accumulates 100, the mahi-mahi accumulates 1,000.
By the time you reach the predators at the very top of the food web, the apex predators like sharks, toothed whales, and our sea turtle, they are absorbing the absolute highest concentrations of this material.
This compounding effect is known as bioaccumulation.
And the story of the Laysan albatross chicks on Midway Atoll is one of those heartbreaking visual representations of this in the world.
It really is. Wildlife photographers have documented it extensively.
The parents, driven by millions of years of instinct, regurgitate what they fully believe is a nutritious meal into the mouths of their babies.
But it's not squid. It's bottle caps, disposable lighter casings, and jagged shards of broken toys.
The chicks' small stomachs physically fill up with this indigestible, bulky material.
They sit on their nest feeling completely satiated and full, but they are literally starving to death because there is no physical room left in their digestive tracts for actual calories or nutrition.
It is a devastating illusion of satiety. And it's not just an anecdotal tragedy. We now have sobering, hard mathematical data on exactly what it takes for this material to be lethal.
Yeah, recent comprehensive studies analyzed over 10,000 animal necropsies across multiple marine species to determine the threshold of toxicity.
And the physical amounts required to kill an animal are shockingly small. I read the data on the seabirds. For a bird like an Atlantic puffin, swallowing just 3 sugar cubes worth of this synthetic material constitutes a 90% fatal dose.
Just 3 sugar cubes.
Just 3.
And for a robust, armored animal like the loggerhead sea turtle we are following, half a baseball's worth of accumulated material in the gut is a 50% fatal dose.
Half a baseball. For an ancient, powerful animal that can grow to weigh hundreds of pounds and crush conch shells with its jaws.
It's terrifying.
But let's dig deeper into the mechanics of why it's fatal. Because it's not just the physical blockage, the impaction, or the tearing of the stomach lining.
No, not at all.
It's what the material brings with it into the animal's body.
Precisely. We have to discuss the chemical hitchhiker problem.
Chemical hitchhikers?
Yeah. These synthetic fragments don't just act as physical obstructions. They act like microscopic hydrophobic sponges.
Okay.
As they drift through the ocean for years, they aggressively soak up ambient toxins from the seawater, specifically a class of chemicals called persistent organic pollutants, or POPs.
We're talking about heavy-duty industrial legacy chemicals, things like PCBs used in old electrical equipment, and agricultural pesticides like BDT that were banned decades ago but still linger in the oceanic environment.
Yes, exactly. Because both the plastics and these toxic chemicals are hydrophobic, meaning they repel water. They naturally bind together.
So they attract each other.
Right. A single microplastic fragment can absorb and concentrate these toxins up to 1,000,000 times their normal background level in the surrounding seawater.
1,000,000 times.
It becomes a highly toxic poison pill.
And when a sea turtle or whale swallows that pill, the warm, highly acidic environment of their stomach acts as a solvent.
It breaks the bonds, releasing those concentrated toxins directly into the animal's bloodstream and fatty tissues.
And tragically, they get a double dose of poison.
How so?
Well, they're exposed to the ambient chemicals that hitchhiked on the outside of the fragment, plus the inherent chemical additives like BPA, phthalates, and flame retardants that were blended into the plastic during manufacturing to make it flexible or durable,
Ah, right. Both sets of chemicals leach into the animal.
disrupting their endocrine systems, suppressing their immune systems, and drastically lowering their reproductive success.
It is deeply horrifying to realize that the apex predators, the magnificent whales, the soaring albatross, our ancient sea turtles, the animals that define the wildness of the ocean, are bearing the absolute heaviest burden of this invisible toxic chain.
They are the unwitting reservoirs of our chemical legacy.
But what about the material that doesn't stay suspended on the surface for the birds and the turtles?
Right. What happens to the billions of fragments that undergo biofouling, getting pulled down by that heavy bacterial slime we discussed earlier?
To see that, we have to guide our loggerhead turtle downward. She takes a massive, deep breath of surface air, points her head toward the bottom, and dives.
The light begins to fade as she glides down into the mesopelagic loam, eventually passing over a vibrant, bustling coral reef structure jutting out from a seamount.
We watch as the tiny coral polyps, the soft, living, anemone-like creatures that secrete the hard calcium carbonate skeletons forming the very foundation of the reef, extend their delicate, feathery tentacles into the current to feed.
And they are blind,
Right.
relying entirely on chemical receptors to find food.
Exactly. And as the bacteria-coated microplastics rain down from the surface, the corals are tricked by the chemical signature of the biofilm.
They grab the synthetic fragments with their tentacles, pull them into their mouths, and ingest them, fully believing they are eating nutritious marine snow.
And coral reefs are the bustling metropolises of the ocean, housing roughly 25% of all marine biodiversity.
So when these foundational organisms ingest these fragments, what happens to them biologically?
It is disastrous. The sharp edges of the microplastics can physically lacerate the delicate internal tissues of the coral polyp.
Ouch.
Furthermore, the bacteria writing on the plastic often contain pathogens. Ingesting this material triggers severe inflammation, tissue necrosis, and massive immune stress.
It makes the coral highly susceptible to diseases like white syndrome, effectively rotting the foundation of the ocean's greatest apartment building from the inside out.
And the material that misses the reef just keeps falling.
It continues its slow, silent descent past the twilight zone into the freezing, pitch-black, crushing abyss of the bathypelagic zone.
It joins the authentic marine snow, the gentle, perpetual falling shower of organic matter, dead plankton, and fecal pellets that sustains life in the deep sea.
Scientists have deployed submersibles and found this synthetic material at the very bottom of the Mariana Trench, nearly 11 kilometers beneath the surface.
The deepest, most inaccessible place on planet Earth, and our synthetic exhaust is already there.
The deep sea is actually the ultimate final sink for this pollution.
Current estimates suggest the ocean floor is holding anywhere from 3 to 11 million tons of this material.
Biologists have sampled centuries-old deep-sea corals and slow-moving abyssal sea cucumbers and found their tissues laced with microplastics.
The deep ocean is quietly hoarding the bulk of the crisis.
You know, when we talk about the deep ocean, it can feel so incredibly disconnected from our daily lives on land. It feels like an alien world.
Oh, absolutely.
But there is a massive overarching climate connection tying this all together, isn't there?
A profound and often overlooked one. We have to remember where this material originates. 99% of all synthetic plastics are born from fossil fuels extracted crude oil, natural gas, and coal.
The industrial process of refining these fossil fuels and cracking them into polymers releases massive, staggering amounts of greenhouse gases into the atmosphere.
The creation, transportation, and eventual degradation of this material is fundamentally part of the exact same carbon cycle that is altering the thermal equilibrium of the entire planet.
Which brings us to a stunning, almost unbelievable biological feedback loop that directly impacts our loggerhead turtle.
Oh, this part is wild. Let's fast forward and return to her perspective.
She is a mature adult now. After decades of navigating the vast ocean currents, an ancient magnetic map encoded in her brain calls her back to the shore.
She navigates thousands of miles, returning to the exact same stretch of beach where she hatched all those years ago.
Under the cover of darkness, she hauls her massive, heavy body up the sand, digs a deep, teardrop-shaped chamber with her rear flippers, and lays a clutch of 100 leathery eggs.
But the beach she has returned to has fundamentally changed.
The sand is no longer just crushed shells and coral.
Decades of ocean currents have washed millions of tiny, degraded synthetic fragments ashore, mixing them deep into the substrate of the beach.
And because these plastic fragments are often dark-colored blacks, blues, and dark greens, they absorb and retain the sun's radiant heat far more efficiently than natural light-colored sand.
They alter the thermal conductivity of the beach itself, warming the sand surrounding her buried nest.
And here's the evolutionary kicker. For a sea turtle, genetic sex is not determined by chromosomes at conception.
No, it is determined by the ambient temperature of the sand during the middle third of incubation.
It's a process called temperature-dependent sex determination. The biological rule of thumb is cool dudes and hot chicks.
Warmer sand produces female hatchlings. Cooler sand produces males.
And because the microfragments mixed into the beach are literally changing the localized temperature of the Earth, acting as tiny heat sinks, they are artificially raising the incubation temperature of the nests.
This is actively skewing the sex ratios of future generations of sea turtles, producing dangerously female-biased populations.
In some highly polluted and warming regions, populations are turning 99% female.
Which poses an existential threat to their long-term genetic viability.
Think about the terrifying interconnectedness of that.
Yeah.
The mechanical shear of a tire wearing down on a rainy city street in Seattle washes into a river, floats out to a Pacific gyre, gets baked by the sun, washes onto a remote nesting beach in the Pacific Islands, absorbs solar radiation, and fundamentally alters the biological destiny of a sea turtle species that has survived since the time of the dinosaurs.
The entire planet is inextricably tethered together. Every local action cascades globally.
And that tether doesn't just span the saltwater of the ocean. It reaches up into the sky, it blankets the highest alpine mountains, and it drifts right into the airspace of our own living rooms.
To understand how, let's follow our loggerhead turtle as she surfaces from a deep foraging dive.
She breaks the tension of the water, opens her nostrils, and exhales a massive rushing breath of air.
The wind blowing violently across the surface of the water in that moment has traveled thousands of miles across whole continents.
If we could pause time and use a microscopic lens to view the air whipping past her face, we wouldn't just see sea spray and oxygen.
We would see thousands of tiny, weightless synthetic fibers riding the breeze.
Because the story of this material extends far beyond the boundaries of the ocean.
The churning action of the waves, combined with the wind, actually aerosolizes these tiny fragments, launching them out of the water and into the atmosphere.
Atmospheric currents catch them and carry them everywhere.
Scientists have set up pristine catch basins high in the remote French Pyrenees Mountains, miles away from any city, and found microplastics falling gently in the rain.
They are trapped deep in the remote, untouched snows of the Arctic Circle.
And incredibly, they have been found floating directly inside the clouds.
I was reading a recent atmospheric study where scientists scaled Mount Fuji in Japan, venturing into the high-altitude cloud cover.
Yes, the researchers sampled the condensed cloud water at the summit, far above the tree line.
And they found airborne polymers suspended in the moisture.
But it wasn't just passive pollution. They discovered that these microplastics might actually be acting as cloud condensation nuclei or ice nucleating particles.
Wait, really? For those who haven't taken a meteorology class recently, clouds don't just form out of thin air?
No, water vapor needs a microscopic physical surface, a seed, to cling to in order to condense from a gas into a liquid droplet.
Historically, those seeds were natural dust, volcanic ash, or sea salt.
But now, atmospheric microplastics are providing that surface.
Which implies that our synthetic exhaust isn't just riding in the clouds. It could literally be dictating the formation of clouds, altering precipitation cycles, and fundamentally changing global weather patterns.
That is a deeply humbling, almost paradigm-shifting realization.
It means the boundary between the natural world and our synthetic world has completely dissolved.
We are a part of this ecosystem too. We breathe these airborne fibers every single day in the household dust, swirling in sunbeams in our living rooms, shed from our own synthetic carpets, couches, and clothing.
We ingest them in our municipal drinking water, and even in the food we eat.
We absolutely do. We are inhaling and ingesting the very environment we have created.
But as we acknowledge our own exposure, we must also shine a light on the profound human element of environmental justice.
Because the burden of this cycle is distributed incredibly unfairly across the globe.
Let's talk about the island nation of Tuvalu. I was looking into a case study on them, and it shifts this from an ecological issue to a severe crisis of environmental justice.
Tuvalu is a tiny, low-lying Pacific island nation. They have a population of fewer than 12,000 people.
From an industrial standpoint, they produce almost zero synthetic waste.
They do not manufacture plastics. They live a largely sustainable, localized lifestyle.
Yet, because of the inescapable physics of the ocean currents we discussed earlier, the ocean's global conveyor belt treats their pristine beaches like a dumping ground.
They receive the world's discarded fragments on their shores, pushed in by the tides every single day.
They have a landmass of just 26 square kilometers. They literally have no physical space for landfills.
They didn't create the crisis. They didn't benefit from the industrial boom that produced the material. Yet they are forced to live on the front lines of its most devastating consequences.
They share this burden alongside millions of informal waste workers around the globe. Individuals who spend their lives wading through toxic material, sorting through our discarded waste by hand, often in hazardous conditions, just to survive on the margins of the global economy.
When you zoom out and look at the sheer scale of the problem, it's in the highest alpine clouds, it's 11 kilometers down in the Mariana Trench, it's altering the sex of ancient reptiles, and it's smothering innocent island nations. It feels completely insurmountable.
It's easy to feel a sense of eco-paralysis. How do we even begin to turn the tide against an invisible enemy that is literally everywhere?
It is vast, yes, but it is unequivocally not insurmountable. The human capacity for destruction is matched only by our capacity for innovation.
Right now, there are brilliant minds, relentless engineers, and deeply passionate grassroots communities refusing to accept this dystopia as the end of the story.
Let's look through our loggerhead turtle's eyes one last time, swimming near a densely populated coastline.
She navigates toward a river mouth, expecting the same murky, toxic plume we saw earlier.
But this time, instead of an unchecked flow of terrestrial debris rushing into the sea, she swims past a massive, slow-moving marvel of engineering.
It's a high-tech floating barrier stationed right in the current, gently but firmly scooping the material out of the water, channeling it onto a conveyor belt, and extracting it before it can ever reach the open ocean.
That is the famous bathtub analogy in action.
A bathtub analogy.
Yeah, if you walk into your bathroom and find the bathtub overflowing, flooding the floor, you have to do two things simultaneously.
You must grab a mop to clean up the mess that has already been made.
But crucially, you must reach up and turn off the tap to prevent more water from pouring in. You cannot mop effectively if the tap is still running.
Let's talk about the mopping first, the massive cleanup efforts. I am endlessly inspired by the story of the ocean cleanup.
It's a phenomenal story of persistence. It started with a teenager named Boyan Slat.
He was a 16-year-old on a scuba diving trip in Greece, and he looked around and realized he was seeing more plastic bags than fish.
He had a radical, seemingly impossible dream. Instead of chasing trash around the ocean with boats and nets, which takes massive amounts of fossil fuels, why not design a passive system that uses the ocean's own natural currents to collect the floating fragments?
And the scientific community initially told him it was impossible. They said the forces of the ocean would tear his equipment apart.
But he didn't stop. He raised funds, hired engineers, and his dream became a tangible reality.
His organization has now successfully removed over 50 million kilograms of material from the ocean.
They deploy these massive U-shaped floating barriers, sometimes half a mile long, that sweep the surface currents of the gyres.
And crucially, they realized that just sweeping the ocean wasn't enough. They had to go to the source.
So they designed a fleet of solar-powered river interceptors. They are deploying these autonomous high-tech barges in some of the world's most heavily polluting rivers in Southeast Asia and the Americas, catching thousands of tons of material every day before it ever hits the saltwater.
And they aren't alone in the riverways. In Baltimore, Maryland, there is a brilliant, localized solution affectionately known as Mr. Trash Wheel.
It is a solar and hydro-powered interceptor built right into the river mouth.
The creators gave it these giant, cartoonish, googly eyes, turning it into a beloved local mascot.
The community rallies around it, and it has gobbled up thousands of tons of river debris, preventing it from ever reaching the Chesapeake Bay.
Engineering is a vital tool, but the most powerful force for change is often human passion. It's the youth action.
Look at the story of Malati and Isabel Wiesen in Bali.
That is one of my favorite stories. They were just 10 and 12 years old when they looked at the pristine beaches of their island home being smothered by daily tides of trash.
Instead of waiting for adults to fix it, they started a grassroots campaign called Bye Bye Plastic Bags.
They organized massive beach cleanups, they marched, they spoke at international summits, they even went on a highly publicized hunger strike to get the attention of the governor.
And their relentless pressure worked. These two children successfully pushed the local government to change the laws of their entire island, leading to a comprehensive ban on single-use plastics in Bali.
They proved that you do not need a PhD to effect massive systemic change.
Absolutely. And as we tackle the visible trash, we are also finding solutions for the invisible threats.
Let's go back to the washing machines. We talked about the hundreds of thousands of microfibers shedding from our fleece jackets.
Well, France recently passed a revolutionary legislative mandate.
Beginning in 2025, every single new washing machine sold in the country must be equipped with a specialized microfiber filter.
It's a simple, elegant policy shift. It treats the washing machine like the exhaust pipe of a car, catching those microscopic fibers right at the source before they ever leave the house and enter the water treatment system.
And perhaps the most awe-inspiring breakthroughs are happening at the microscopic level. If bacteria can learn to attach to this material in the ocean, can they learn to eat it?
Back in 2016, Japanese scientists were studying the soil outside a bottle recycling facility, and they discovered a strain of bacteria, Ideonella sakensis, that had naturally evolved the ability to use peat plastic as its primary energy source.
Nature was fighting back.
Building on that discovery, researchers have now engineered an incredibly efficient enzyme called phosphatase.
And this isn't just breaking it down into smaller, invisible microplastics, right?
No, it is a complete chemical depolymerization. The enzyme acts like a pair of molecular scissors.
It physically cleaves the strong chemical bonds of the polymer chain in a matter of days.
If you imagine the plastic structure as a massive, complex Lego castle, the enzyme doesn't just smash the castle, it meticulously takes it apart piece by piece until you are left with nothing but the original, harmless, raw monomer blocks again.
Those blocks can then be used to build a new bottle, creating a truly closed-loop, circular system that requires no new fossil fuels.
So the narrative is shifting. It's not just a story of doom and inevitable pollution.
It's a story of brilliant scientists in state-of-the-art labs, 10-year-old activists in Bali, marine engineers in the Netherlands, and progressive lawmakers all pulling together, utilizing every tool at our disposal to rewrite the ending of this global wildlife documentary.
Exactly. The human capacity for innovation is proving to be as vast and as powerful as the problem itself.
Let's return one final time to our loggerhead sea turtle. She's fully grown now, a massive, ancient, scarred mariner. She is gliding gracefully through the moonlit ocean, suspended in the weightless blue.
The water rushes smoothly over the golden geometric plates of her shell. Her powerful flippers beat in a slow, hypnotic rhythm.
She is riding ancient, invisible currents, following the magnetic pull of a vast, interconnected world she has navigated for decades.
But the clarity of her waters in the years to come, the safety of the prey she hunts, and the temperature of the sand where her descendants will hatch depends entirely on the choices being made on land right now in this very moment.
The ocean is not a distant, separate world. It is not in a way where we can throw things and forget them.
Everything is connected. Every breath we take in our living rooms, every synthetic jacket we wash in the cold, every tire that grips the road, and every drop of rain that falls on the highest mountain connects us directly to the water she swims through.
We're not just observers of her environment. We're the active authors of her ocean. Thank you so much for floating alongside us today on Saltwater Stories. The currents of our world are deeply, profoundly connected, and so are we. We can't wait for you to join us on our next adventure beneath the waves.